When you buy eggs, it's always a good idea to check them for cracks. It doesn't take very long, and if you've checked each one, you can be absolutely sure that none of them are broken. But in many cases, this sort of exhaustive search just isn't possible. Say you own an egg distribution center, and you get a shipment of 1,000,000 eggs. You want to verify the vendor's claim that only 1% of those are cracked. But maybe you only have time to individually check 1,000 of them before you have to accept or reject the whole shipment. How many bad eggs would you have to find in those 1,000 before sending the rest back? The problem is that you'll never get a clear answer with this test. If you're okay with 1% of all of the eggs being broken, that's 10,000 bad eggs, somewhere within the million. Since you're only looking at 1,000, even if every single egg you check is broken, you still can't say for sure that more than 1% of the whole set is bad. You could have just gotten a wildly unlucky sample. How can we say anything about the full shipment from looking at such a small subset? The idea of a statistical test is to try to figure out what sorts of results we would expect to see under a given assumption. So if we assume that these eggs are 99% whole, how many eggs should we expect to find? And how concerned should we be when we find a different amount? Depending on how unlikely the result is, we might decide to abandon our original assumption. Well, if the overall bad egg rate is really 1%, we should expect to see an average of 10 bad eggs per 1,000. The results will vary, though. We have to choose our sample completely randomly for this to work. We can't just look at eggs from cartons on the bottom layer of a particular truck. We have to make sure that every egg has the same chance of becoming part of our sample. That way the sample is representative of the whole. A truly random selection means we might end up with 0% or 2% of our sample being broken, even if the true overall rate is 1%. If half of the eggs in our sample, 500, were broken, we should probably send the whole thing back. That would seem to be very unlikely if 99% of the eggs in the shipment were really good. But where should we draw this line? How many broken eggs is unlikely enough to decide that the shipment should be sent back? Well, we can actually figure out the chances of seeing any particular number of broken eggs when sampling from a 1% broken shipment. The easiest way to do that today is to get a computer to try it a bunch and take notes. I made this program to simulate our situation. I gave it 1,000,000 eggs, of which 1% are broken, and I've told it to pick random samples of 1,000 at a time. It counts up the broken eggs in each sample and plots them on this graph. We can see that the distribution of results it gets has a particular shape. As we get further from the expected average of 10, there are less and less samples with each particular result. As we simulate more tests, this shape will start to approach some true distribution. That'll be the proportions of broken eggs in the set of all possible ways of choosing 1,000 from this particular shipment. Here are the results of 1,000,000 tests. As you can see, it most often found about 10 broken eggs, just like we expected, but sometimes it got 0, and one time it got 29. In statistical terms, the proportion of broken eggs we see in our sample is called the test statistic. That's the property that we care about in the sample. The overall distribution of possible test statistics is called the sampling distribution. It shows us the range of broken eggs we expect to see with our test if the shipment is really 99% good as advertised. I built this curve just by simulating our test over and over, rather than calculating the exact values using some formula. And that may seem like kind of a hack, but using a model to get a very close estimate can be the best compromise, and many modern statistics programs use a similar approach. So now we have a picture of what we expect to see if 99% of those eggs are really good. We can use this to answer our previous question. How unusual is it to see a particular amount of bad eggs in a sample from a good shipment? Say we find 25 broken eggs, landing us right here on the curve. That's pretty far from the average expectation. What we can do to quantify that is add up all the cases where we saw at least that many broken eggs, all the results to the right of this, and find what percent of the time we expect to see something at least this extreme. As it turns out, there are 49 cases in our 1,000,000 tests where 25 or more broken eggs were found. So we should expect to see something like that 49 out of 1,000,000 times. This number is very important. It's called the p-value. P-values are very often misinterpreted, so let's take a minute to carefully lay out what this really means. We have an assumption about the whole set of eggs, which is called the Null Hypothesis, that 1% are broken. This is what we are going to try to figure out if we should continue to believe with this test. And the test we're doing is a specific test reading out how many broken eggs there are in 1,000, and that number is called the test statistic. We've also calculated the set of possible results we can get with this test and their likelihoods, if that null hypothesis is true, if the eggs are really good. The p-value, then, is just a measure for any given result of how likely it is for us to have found something at least that extreme, at least that far from our average expectation, if our assumption is true. If we were to draw this sampling distribution as a pie chart of our expectations based on the null hypothesis, the p-value would just be the thickness of the slice, representing results at least as extreme as what we got. Importantly, the p-value doesn't give you an answer in itself. You have to judge the p-value based on some standard as to whether it's small enough to force you to change your mind. A p-value of 0.000049 means that we'd only see 25 or more broken eggs in a sample from a good shipment 0.0049% of the time, about 1 in 20,000. So that's low enough that I would feel pretty confident the shipment was below standards, and probably send it back. This judgment, that the test statistic seems so unlikely that our assumption must be wrong, is called rejecting the null hypothesis. It's basically the only thing that the statistical test can let us do actively, and understanding the reasoning behind it is critical to really grasping what these tests do. When we reject an assumption with a statistical test, we're basically making an argument from absurdity. We're saying, under this assumption, this result we're seeing would be super unlikely, to the point that the assumption is unreasonable, and we shouldn't believe it. There's no way that 99% of these eggs are good if I saw 25 bad ones in a sample of 1,000. That's just unreasonable, and so I won't believe it. All you can do with the results of a statistical test like this is either reject or fail to reject your default assumption. You can never confirm or even accept it. If we see 10 broken eggs in our sample, we can't say that this shows 99% of the shipment is unbroken. All we can say is, this wouldn't be weird to see if 99% of the shipment was unbroken, so I'll keep assuming that's the case. Conversely, and I can't stress this enough, even the most extreme test result can't tell us for sure that the shipment is bad. If we only rejected shipments when we saw 29 or more broken eggs, a 1 in a million result if it's actually a good shipment, we'd still accidentally reject 1 in every million good shipments. The specific level of unlikeliness we want to see before rejecting our assumption is called the threshold of significance. And there's no perfect place to put it. We're always going to make some mistakes one way or the other. We have to decide for ourselves what threshold makes sense, and where exactly we draw that line will depend on what kinds of mistakes we'd rather avoid. There are two basic ways we can make mistakes, and they tend to trade off. The first would be getting a particularly bad sample with lots of broken eggs, and thinking there's no way 99% of this shipment is good, even though it actually is, and we just picked an unlucky sample. This is a false positive. We're saying, I think there's something here that I didn't expect, and rejecting our assumption, when really the assumption was correct. The other type of mistake would be failing to notice that the shipment has more broken eggs than we thought, a false negative. We'd see a particularly good sample with few broken eggs and think, this shipment is probably fine, but really there would be more broken eggs total than promised, and we'd have just happened to choose lots of good ones for our test. Moving the threshold of significance around changes the relative likelihood of making these errors. If we only send shipments back when we see 30 or more bad eggs, we'll probably let through a lot of bad shipments. But if we get worried every time we see 11 or more, we'll be rejecting a bunch that are probably actually fine. In the real world, people use a wide range of different significance thresholds, depending on their specific goals. Social scientists often use 0.05 as the threshold, meaning that they reject their default assumption if they see something that they would only predict having seen 1 in 20 times or less. In our case, any more than 15 broken eggs per sample would be sent back. In particle physics, sometimes there are thresholds as small as 1 in 3 million. They would only reject shipments based on a test that showed 30 or more broken eggs. There's no correct place to set a significance threshold, and neither of these standards is objectively better than the other. The choice depends on what you're trying to accomplish with your test, and which kind of error you'd rather make.